What if the fabric of reality itself was written in a language we are only beginning to understand? What if beneath the seemingly solid world we see, there exists a realm where particles can be in two places at once, where information defies intuition, and where probability is not just a concept, but the very foundation of existence? At the heart of this mystery lies an equation, one that has reshaped our understanding of the universe at its most fundamental level. This is Schrödinger's equation, the mathematical backbone of quantum mechanics. It is not merely a formula, it is a map, a guide to the strange and beautiful world of quantum physics. It tells us how particles move, how they interact, and most intriguingly, how reality itself is shaped by probabilities. Without this equation, our comprehension of the universe at its smallest scales would unravel. But what if we could do more than just understand? What if we could harness these quantum principles, not just to study reality, but to build something entirely new? Unlike classical computers, which process information in a rigid, binary fashion, quantum computers embrace uncertainty, complexity, and superposition, mirroring the quantum world itself. They are not just machines, they are a glimpse into the deeper workings of reality, a key to problems once thought impossible to solve. In 1980, physicist Paul Benioff envisioned a machine that didn't rely on traditional bits, but on quantum bits, qubits, tiny units of information that obeyed the strange laws of quantum mechanics. This was the first step toward what we now call quantum computing. At the time, it seemed like science fiction. Classical computers were getting faster, but when physicists tried to use them to simulate quantum systems, they hit a wall. The problem wasn't just speed, it was complexity. The quantum world is exponentially more intricate than what classical computers can handle. This challenge captivated brilliant minds like Yuri Manin and Richard Feynman, who proposed something revolutionary. To truly understand quantum mechanics, we needed computers that worked like quantum systems themselves. Their insights would lay the foundation for a technological revolution, one that would not only redefine computing, but also reshape fields like cryptography, communication, and artificial intelligence. What if the rules we thought governed reality were just an approximation of something deeper? What if the universe, at its most fundamental level, operated on principles so alien to our everyday experience that even our most powerful classical computers struggled to comprehend them? In a world where information has long been defined by simple binary states, zeros and ones, a new frontier is emerging, one that does not just compute, but redefines the very essence of computation itself. This is the world of quantum computing, where probabilities replace certainties, entanglement defies locality, and computational power reaches unfathomable scales. To understand this revolution, we must first explore the fundamental differences between classical and quantum computation. Classical computers have been the backbone of technological progress for decades, driving everything from meteorological modeling to digital photography. At their core, these machines process information using bits, discrete units that can be either a 0 or a 1. Every computational task, no matter how complex, is ultimately reduced to a vast sequence of binary switches flipping between these two states. Consider a meteorological prediction system. The temperature, pressure, humidity, and wind patterns are all converted into binary data, which is then processed through intricate models to forecast the weather. Similarly, in digital photography, each pixel in an image is represented as a series of bits that encode color and intensity. These processes work efficiently because they follow a structured, linear pathway of computation. But what happens when problems become too complex for this step-by-step approach? Some problems grow exponentially in complexity, making them nearly impossible for classical machines to solve within a reasonable time frame. Take molecular simulation, for example. Understanding the behavior of a single molecule requires accounting for the quantum interactions of its constituent atoms, a task that classical computers struggle with because they must process each interaction sequentially. Similarly, optimization problems, such as finding the most efficient routes for delivery trucks, or determining the optimal way to schedule airline flights quickly become intractable as the number of variables increases. Classical computers must evaluate each possibility one at a time, making these tasks inefficient as the complexity scales. Quantum computers, however, operate under entirely different principles. Instead of bits, they use qubits, which exploit the bizarre properties of quantum mechanics to encode information in multiple states simultaneously. This is known as superposition. A single qubit can exist in a combination of both 0 and 1 at the same time, rather than being restricted to just one or the other. This allows quantum computers to perform multiple calculations in parallel. To visualize this, imagine trying to guess a 4-digit PIN. A quantum computer, on the other hand, could evaluate all possible combinations simultaneously, drastically reducing the time needed to arrive at the answer. This is what gives quantum computing its enormous computational advantage. Beyond superposition, quantum computers leverage another phenomenon, entanglement. When two qubits become entangled, their states become linked such that the state of one qubit instantly determines the state of the other, regardless of the physical distance between them. This property allows quantum systems to share and process information in ways that classical computers simply cannot. Entanglement enables quantum computers to solve complex problems with an efficiency that seems almost magical. Instead of processing data in isolation, entangled qubits communicate instantaneously, allowing quantum systems to work as a unified whole. This interconnectedness dramatically enhances computational power and opens new possibilities for fields such as cryptography and material science. A single qubit may not seem impressive on its own, but as more qubits are added, their computational potential grows exponentially. With just 300 qubits, a quantum computer can represent more states simultaneously than there are particles in the observable universe. This level of computational capacity is incomprehensible to classical computing systems, which would require an astronomical amount of memory to achieve the same feat. Today, most secure communication systems rely on encryption methods like RSA, which is based on the difficulty of factoring large numbers. The security of RSA depends on the fact that multiplying two large prime numbers is easy, but reversing the process, factoring the product back into its prime components, is incredibly hard for classical computers. For example, a 2048-bit RSA encryption key is so computationally demanding to break that it would take a classical supercomputer millions of years to solve. However, with quantum computing and Shor's algorithm, this problem becomes trivial. Shor's algorithm allows quantum computers to factor large numbers exponentially faster than classical methods, rendering RSA encryption effectively obsolete. This has led to a race to develop post-quantum cryptography, encryption techniques that remain secure even in the presence of quantum attacks. Beyond cryptography, quantum computers excel in optimization problems, finding the most efficient solutions from an overwhelming number of possibilities. Consider logistics. Companies like FedEx and Amazon rely on complex routing algorithms to optimize delivery paths. While classical computers can approximate solutions, they cannot process all possibilities at once. Quantum computers, however, can explore all potential routes simultaneously, identifying the most efficient path almost instantly. This capability could revolutionize industries ranging from transportation to finance, enabling unparalleled efficiency gains. Despite their immense potential, quantum computers are not a replacement for classical machines. They are not universally better. Rather, they excel at specific types of problems that involve massive complexity and parallel computation. Everyday tasks, such as checking emails, browsing the web, or running spreadsheets, remain firmly within the domain of classical computing. Running a quantum computer for these mundane tasks would be akin to using a spaceship for a daily commute, overkill and highly impractical. Moreover, the current state of quantum hardware presents significant challenges. Qubits are fragile, highly susceptible to interference from their environment, and require extreme conditions, such as temperatures near absolute zero, to function properly. Error correction remains one of the biggest obstacles to scaling quantum computers for practical applications. Without breakthroughs in stability and fault tolerance, quantum computers will remain confined to highly specialized uses. Most quantum computers today are still in the experimental phase. Companies like Google, IBM, and Rigetti Computing are developing quantum processors, but these systems currently have limited practical applications. Google's Sycamore processor, for instance, was able to perform a calculation in minutes that would take the fastest supercomputers thousands of years. However, such demonstrations remain highly specialized and not yet applicable to everyday computing needs. At the same time, artificial intelligence has been making its own leaps forward, raising the question of whether AI and classical computing might solve some of the same problems once thought to require quantum computing. AI excels at pattern recognition and learning from vast datasets, while quantum computing is uniquely suited for problems involving complex system interactions. Rather than competing, these technologies will likely complement each other, each bringing its own strengths to the table. Some physicists, like Seth Lloyd, have even speculated that the universe itself may function like a quantum computer. If every interaction between particles represents a fundamental computation, then quantum mechanics might be the key to understanding the very fabric of reality. Recent experiments using quantum processors, such as simulations of wormhole-like behavior, hint at the potential of quantum computing to model some of the most profound mysteries of physics. This experiment underscores a deeper idea that quantum computing is not merely a technological breakthrough, but a conceptual revolution. The principles that underpin quantum computation, superposition, entanglement, and quantum interference, mirror the very laws that govern the universe at its most fundamental level. Theoretical physicist Seth Lloyd once proposed that the universe itself may be a vast quantum computer, where every particle interaction represents a fundamental computation. From the spin of an electron to the evolution of galaxies, reality might unfold as a vast ongoing quantum calculation. While this notion remains speculative, it serves as a compelling framework for understanding both quantum computing and the universe itself. Unlike classical computation, which follows a linear, step-by-step progression, quantum mechanics suggests that reality explores multiple potential outcomes simultaneously before collapsing into a single observed state. This eerie parallel between computation and existence fuels some of the most profound philosophical questions in modern physics. As we advance in our pursuit of quantum computation, we must temper our expectations with a clear understanding of its limitations. Quantum computers are not destined to revolutionize everyday computing. They will not replace our laptops, stream our favorite shows, or run consumer applications. Their role is far more ambitious: to tackle the unsolvable, to simulate the unimaginable, and to probe the very foundations of reality. If successful, they could redefine our understanding of materials, medicine, artificial intelligence, and even the nature of the cosmos. In the grand scheme of technological progress, quantum computing is not a convenience. It is an expedition. It will not make life simpler, but it may reveal truths that have eluded us for centuries. It will not replace classical computers, but it will expand the boundaries of computation in ways we are only beginning to fathom. And in doing so, it might just unlock the deepest secrets of the universe itself. If that is not extraordinary, what is? In our everyday lives, the laws of the universe feel comforting, simple, and reliable. These laws govern everything around us, from the flow of water to the motion of objects. Imagine standing by a river. You know the water will flow downhill. If you throw a stone into the air, you can easily predict the trajectory of its fall. Gravity, inertia, and motion are concepts we learn early in school, and they explain much of what we see. Similarly, when you heat a filament in a light bulb, it starts to glow. At first, it emits a dull red light, but as it gets hotter, the light shifts to a brighter orange, then yellow. These changes are predictable and follow the rules of classical physics, a framework that has guided human understanding for centuries. These laws make the universe feel logical, ordered, and accessible. But what happens when we look closer? much closer, into the microscopic building blocks of reality. At this level, the certainty we take for granted disappears, replaced by something almost incomprehensible. Welcome to the world of quantum mechanics, where the rules are not just different, they're bizarre. In this strange realm, particles of matter can exist in two places at once. Their behavior is dictated by probability rather than certainty, and their very existence seems to depend on whether or not they are being observed. Suddenly, the solid foundation of classical physics crumbles. A paradox emerges. For scientists, this was a shocking revelation. They had grown accustomed to a universe that operated predictably, where cause and effect reigned supreme. But at the smallest scales of matter, particles refused to follow these familiar rules. The more they explored, the more they realized that this microscopic world was unlike anything they had ever imagined. As one of the founding fathers of quantum mechanics, Niels Bohr, once said, "Everything we call real is made of things that cannot be regarded as real." In other words, the very fabric of reality, at its most fundamental level, defies our common sense. This discovery marked the beginning of a journey into the unknown, a journey that would challenge the very nature of our understanding of reality itself. The humble beginnings, a problem with the light bulb. At the turn of the 20th century, the light bulb was a symbol of progress, innovation, and modernity. It illuminated homes, powered industries, and revolutionized the way people lived. Yet, this seemingly simple invention posed a question that would baffle scientists for decades. Engineers of the time understood that when an electric current heated a filament, it glowed, producing light. However, the underlying physics of this process was a mystery. Why did the color of the light change as the filament got hotter? Why did it transition from red to orange, yellow, and white, but never to blue or ultraviolet, even at extremely high temperatures? This mystery became known as the ultraviolet catastrophe, a dramatic name for an equally dramatic problem. According to the classical physics of the time, as the filament's temperature increased, the intensity of light at higher frequencies, like ultraviolet, should grow infinitely. But in reality, this didn't happen. The filament emitted very little ultraviolet light, no matter how hot it became. This discrepancy wasn't just a minor annoyance for engineers, it was a fundamental challenge to the laws of physics. And it was here, in the pursuit of understanding the behavior of light in a light bulb, that the seeds of quantum mechanics were sown. Max Planck's revolutionary discovery. Enter Max Planck, a brilliant but pragmatic German physicist. In 1900, Planck was tasked with solving the problem of black-body radiation, the emission of light from an idealized object heated to a specific temperature. Planck proposed that energy is not emitted continuously, as classical physics suggested, but in discrete packets called quanta. These quanta were tiny, indivisible units of energy, and their size depended on the frequency of the radiation. At first, Planck saw this idea as a mathematical trick rather than a groundbreaking insight. He himself admitted that the concept was an act of desperation, a last resort to fit the experimental data. But the implications of his discovery were profound. Planck's work solved the problem of black-body radiation, but it raised more questions than it answered. Why was energy quantized? What did these quanta represent? And what did this mean for the nature of light and matter? The scientific community was intrigued but hesitant. Quantization seemed to violate everything they knew about the continuous nature of energy and waves. Yet, experimental evidence was undeniable. Slowly, Planck's radical idea began to gain traction. The concept of quantization didn't just explain black-body radiation, it challenged the very foundations of physics. If energy could exist in discrete packets, what else in the universe might be quantized? This realization opened the door to a new way of thinking, one that would soon reveal the true nature of light, electrons, and the building blocks of reality itself. But the journey was just beginning. Another phenomenon, equally puzzling, was about to push science even further into the quantum realm, the photoelectric effect. While Max Planck's discovery provided the theoretical framework for quantization, it was Albert Einstein who would take the next critical step. In 1905, Einstein applied the idea of quanta to light itself, explaining a phenomenon that classical physics couldn't, the photoelectric effect. This discovery would not only solidify the concept of quanta, but also earn Einstein the Nobel Prize. The photoelectric effect and Einstein's leap. At the turn of the 20th century, the scientific community was grappling with a phenomenon that defied explanation: the photoelectric effect. It was a simple enough observation. When light struck certain metals, it ejected electrons from the surface. Yet the process behaved in ways that were completely inconsistent with the classical wave theory of light. According to existing theories, light was a continuous wave, and its energy should depend solely on its intensity. A brighter light source, regardless of color, should transfer more energy to the metal, dislodging electrons more effectively. But experiments repeatedly proved otherwise. Red light, no matter how bright, could not knock electrons loose, while even a faint beam of ultraviolet light could do so effortlessly. Moreover, the ejection of electrons occurred instantly, as soon as the ultraviolet light made contact with the metal surface. This was baffling. If light behaved as a continuous wave, the energy should build up over time, like water gradually heating a kettle. But the reality was far different. In 1905, a young Albert Einstein proposed an idea that would revolutionize science. Building on Max Planck's earlier work on quantized energy, Einstein suggested that light was not a continuous wave, but a stream of discrete packets, or particles, which he called quanta. Today, we know them as photons. Each photon carried a specific amount of energy, determined by the frequency of the light. High-frequency light, such as ultraviolet, carried more energy per photon, while low-frequency light, like red light, carried less. This, Einstein argued, was the key to the photoelectric effect. When a photon struck the surface of a metal, it transferred its energy to an electron. If the photon's energy was high enough to overcome the electron's binding energy, the electron would be ejected from the metal. If not, no amount of additional photons or light intensity could dislodge the electron. This was why red light, even at high intensities, failed to knock electrons free, while ultraviolet light, despite its lower intensity, succeeded with ease. The process was instantaneous because it depended on a single collision between a photon and an electron, not on the gradual accumulation of energy. Einstein's explanation was as elegant as it was revolutionary. It resolved the mysteries of the photoelectric effect, but it also challenged long-standing beliefs about the nature of light. For centuries, scientists had debated whether light was a wave or a particle. Experiments with diffraction and interference clearly showed that light behaved like a wave. But now, Einstein's work revealed that light could also behave like a particle. This duality would become one of the defining features of quantum mechanics, reshaping our understanding of the universe. As we delve deeper into this story, we'll explore how these discoveries about light and matter transformed not just science, but our entire understanding of reality. The paradoxes of the quantum world, from wave-particle duality to the nature of measurement and observation, would become the focus of intense debate and groundbreaking research. These ideas would lead to experiments that defied logic, challenged intuition, and ultimately changed the course of human knowledge. Wave-particle duality of matter and light. The idea that light exhibits both wave-like and particle-like properties was revolutionary, but it was only the beginning. What if this strange duality wasn't unique to light? What if the fundamental particles of matter also behaved in ways that defied conventional understanding? This question led to one of the most iconic experiments in the history of physics, an experiment that forever changed our perception of reality, the double-slit experiment. In classical physics, matter and light were thought to be fundamentally different. Matter consisted of particles, tiny and indivisible, like billiard balls. Light, on the other hand, was a wave, spreading out through space like ripples on the surface of a pond. But as scientists delved deeper into the quantum realm, these distinctions began to blur. The double-slit experiment, first performed with light in the early 1800s by Thomas Young, was a cornerstone of wave theory. In this experiment, light passed through two parallel slits and created an interference pattern of alternating bright and dark bands on a screen behind the slits. This pattern could only be explained if light behaved as a wave, with the peaks and troughs of the waves interacting to either reinforce or cancel each other out. When light behaved like this, it was undeniable evidence of its wave-like nature. However, in the 20th century, scientists began to wonder if particles of matter, such as electrons, might produce a similar result. After all, if light could act as both a wave and a particle, why couldn't matter? To test this, researchers adapted the double-slit experiment for electrons, firing them one by one through the slits and onto a detection screen. At first, the results seemed straightforward. Each electron appeared on the screen as a single point, as one might expect from a particle. But as the experiment continued, a strange pattern began to emerge. When enough electrons had been fired through the slits, an interference pattern identical to the one produced by light waves appeared on the screen. This was astonishing. It was as if each individual electron, traveling through the slits one at a time, somehow passed through both slits simultaneously and interfered with itself. This behavior seemed impossible to explain. If electrons were particles, how could they produce an interference pattern? And if they were waves, how could they arrive at the screen as distinct points? The results defied classical logic, forcing physicists to confront the bizarre reality of quantum mechanics. Niels Bohr, one of the pioneers of quantum mechanics, embraced this idea. According to his Copenhagen interpretation, particles like electrons don't have definite properties or locations until they are observed. Instead, they exist as a cloud of probabilities, with the act of measurement collapsing those probabilities into a single reality. This interpretation was both elegant and unsettling, challenging the very nature of what we consider real. Albert Einstein, however, was deeply dissatisfied with this view. He famously asked, "Does the moon cease to exist when I stop looking at it?" For Einstein, the idea that reality depended on observation was unacceptable. He believed there must be hidden variables, underlying factors that determine the behavior of particles, but were simply unknown to scientists. This disagreement between Einstein and Bohr sparked decades of debate, with each defending their interpretation of quantum mechanics. The double-slit experiment and the concept of wave-particle duality have reshaped our understanding of reality. They challenge the classical view of a deterministic universe where everything follows a predictable path. Instead, the quantum world is governed by probabilities, superpositions, and entanglements, where particles can be connected across vast distances and time itself seems malleable. For many, these ideas are unsettling, even disturbing. They force us to confront the limits of human understanding and question the very nature of existence. Yet they are also a source of wonder and inspiration, revealing a universe far more complex and fascinating than we ever imagined. The journey into the quantum realm is far from over. With each experiment, we uncover new layers of mystery, challenging our assumptions and expanding the boundaries of knowledge. As we continue to explore the strange and beautiful world of quantum mechanics, we are reminded of one of the most profound truths of science. The more we learn, the more we realize how much we don't know. Quantum entanglement and Einstein's objections. The quantum world is a place of endless surprises, but few discoveries have been as mind-bending as the phenomenon of quantum entanglement. At its heart, entanglement is a mysterious connection between particles, one that defies all conventional notions of space and time. For Albert Einstein, this was a step too far, a challenge not only to physics but to the very fabric of reality itself. Entanglement arises naturally in quantum mechanics. When two particles interact, their properties can become intertwined, so deeply connected that the state of one particle directly determines the state of the other, no matter how far apart they are. If you measure one particle and find it spinning in a certain direction, the other particle will instantly adopt a complementary spin, even if it's on the other side of the universe. This immediate connection between entangled particles seemed to imply faster-than-light communication, something Einstein famously called spooky action at a distance. In 1935, he collaborated with physicists Boris Podolsky and Nathan Rosen to publish a paper now known as the EPR paradox. In it, they outlined their objections to quantum mechanics, using a thought experiment to highlight the apparent absurdities of entanglement. Imagine two particles are created in a single event and then separated by a vast distance. According to quantum mechanics, measuring one particle instantly determines the state of the other. But how could this happen? How could one particle know what was happening to its twin without any communication? For Einstein and his colleagues, the only logical conclusion was that the particle's properties were predetermined, encoded at the moment of their creation. The EPR paradox sparked intense debate among physicists. Niels Bohr, a staunch defender of quantum mechanics, rejected the idea of hidden variables. He argued that entanglement didn't involve faster-than-light communication or pre-existing properties. Instead, it reflected the fundamental interconnectedness of the quantum world. In Bohr's view, the act of measurement didn't just reveal information about a particle, it actively shaped reality, collapsing the wave function into a definite state. This interpretation, known as the Copenhagen interpretation, was as radical as it was counterintuitive. It suggested that reality itself was not fixed but fluid, dependent on observation. For decades, the debate remained unresolved. Entanglement was a theoretical prediction, something that could be described mathematically, but not tested experimentally. It wasn't until the 1960s that a physicist named John Bell developed a way to settle the question once and for all. Bell's theorem provided a framework for testing whether hidden variables could explain the behavior of entangled particles. His work led to the development of Bell's inequalities, a set of mathematical relationships that any theory relying on hidden variables would have to obey. In the 1970s, physicists began conducting experiments to test Bell's inequalities, using advanced technology to create and measure entangled particles. The results were astonishing. Time and again, the experiments violated Bell's inequalities, proving that hidden variables couldn't account for the behavior of entangled particles. Instead, the results confirmed the predictions of quantum mechanics, showing that entangled particles were indeed connected in a way that transcended space and time. These experiments had profound implications, not just for physics, but for our understanding of reality. They demonstrated that the universe is fundamentally non-local, meaning that events in one place can influence events in another, regardless of the distance between them. This non-locality isn't just a theoretical curiosity, it's a deeply ingrained feature of the quantum world. It challenges our classical intuition, forcing us to reconsider our notions of separateness and causality. For Einstein, the results were bittersweet. He lived to see his ideas about hidden variables discredited, but he never fully accepted the implications of entanglement. Until his death, he remained convinced that there must be a deeper, more intuitive explanation for the strange behavior of the quantum world. In his words, God does not play dice with the universe. But as the evidence mounted, it became clear that the universe was far stranger and far more fascinating than anyone had imagined. Entanglement isn't just a theoretical curiosity, it has real-world applications that are shaping the future of science and technology. Quantum cryptography, for example, uses entangled particles to create unbreakable codes. Because any attempt to intercept or measure the particles would disrupt their entanglement, it's impossible for eavesdroppers to access the information without being detected. This has the potential to revolutionize cybersecurity, providing a level of security that classical encryption methods can't match. Quantum entanglement is also the foundation of quantum computing, a field that promises to transform the way we process information. Unlike classical computers, which use bits to represent data as ones or zeros, quantum computers use qubits, which can exist in superpositions of both states simultaneously. Entangled qubits can perform complex calculations at incredible speeds, solving problems that would take classical computers millions of years to complete. From drug discovery to climate modeling, the potential applications of quantum computing are virtually limitless. But perhaps the most profound implication of entanglement is its challenge to our understanding of reality. In the classical world, objects are distinct and independent, each existing in its own place and time. But in the quantum world, entanglement blurs these boundaries, revealing a universe where everything is interconnected. This isn't just a philosophical abstraction, it's a measurable, testable fact, one that forces us to confront the limits of our intuition and embrace a new, more complex vision of the cosmos. Entanglement also raises intriguing questions about the nature of time and causality. In some interpretations of quantum mechanics, the connections between entangled particles suggest that the future can influence the past, or that time itself may be an emergent property rather than a fundamental feature of reality. These ideas are still the subject of intense debate, but they hint at a deeper, more mysterious layer of the universe, one that we are only beginning to explore. The story of quantum entanglement is a testament to the power of human curiosity. It began as a thought experiment, a challenge to the foundations of physics, and grew into one of the most exciting frontiers of modern science. It has taught us that the universe is not as simple as it seems, that reality is not always intuitive, and that the act of observing the world can change it in ways we are only starting to understand. As we continue to unravel the mysteries of the quantum realm, we are reminded of the words of physicist Richard Feynman. If you think you understand quantum mechanics, you don't understand quantum mechanics. This isn't a statement of despair, but a celebration of the unknown. It's an invitation to keep asking questions, to keep probing the edges of knowledge, and to embrace the wonder of a universe that is far more complex and beautiful than we ever imagined. Quantum superposition and its implications. The concept of quantum superposition stands as one of the most bewildering and fascinating ideas in the realm of quantum mechanics. It challenges the very essence of what we think we know about existence, forcing us to accept a reality where particles can exist in multiple states simultaneously until they are observed. This idea is not just theoretical. It has been experimentally confirmed and has led to technological advancements that are reshaping the modern world. To understand quantum superposition, consider a single electron. In classical physics, the electron is like a tiny marble that occupies a specific position at any given time. But in the quantum world, the electron doesn't have a single definite location. Instead, it exists as a cloud of probabilities, representing all the possible places it could be. This is what physicists refer to as a superposition. Until we measure the electron, it is not in one place or another. It is everywhere it could potentially be, all at once. One of the most famous thought experiments illustrating superposition is Schrödinger's cat, proposed by Austrian physicist Erwin Schrödinger in 1935. Imagine a cat placed inside a sealed box containing a radioactive atom, a Geiger counter, a vial of poison, and a mechanism that releases the poison if the Geiger counter detects radiation. If the atom decays, the poison is released and the cat dies. If the atom does not decay, the cat remains alive. According to quantum mechanics, until we open the box and observe the system, the atom is in a superposition of decayed and undecayed states. This means the cat is simultaneously alive and dead, a chilling, paradoxical state that defies common sense. Schrödinger's cat was not meant to be a literal experiment, but rather a way to highlight the strangeness of quantum mechanics. It posed a profound question. Does reality exist independently, or is it brought into being by observation? In the quantum world, the act of measurement collapses a superposition into a single outcome. Before observation, the system exists in all possible states. After observation, it snaps into one. This seemingly abstract concept has profound implications for how we understand reality. It suggests that the universe at its most fundamental level is not deterministic but probabilistic. The future is not preordained, it unfolds through a series of probabilities that solidify only when observed. For centuries, scientists believed in a clockwork universe where every event followed inevitably from the one before it. Quantum superposition has shattered that view, replacing certainty with possibility. Superposition is not just a philosophical curiosity, it has practical applications that are driving some of the most exciting technological advancements of our time. At the forefront of this revolution is quantum computing, a field that leverages the principles of superposition to achieve computational power far beyond what is possible with classical computers. In a classical computer, information is stored in bits, which can be either 0 or 1. These bits form the foundation of every computation, from the simplest arithmetic to the most complex simulations. Quantum computers, however, use quantum bits or qubits. Unlike classical bits, qubits can exist in superpositions of 0 and 1 simultaneously. This means a single qubit can perform multiple calculations at once. When you combine multiple qubits, the computational possibilities grow exponentially. For example, with just 300 entangled qubits, a quantum computer could represent more states than there are atoms in the observable universe. Quantum superposition is also being explored in the emerging field of quantum sensing, which uses the delicate nature of quantum states to measure physical quantities with extreme precision. Quantum sensors are already being developed to detect gravitational waves, map underground structures, and monitor biological processes at the cellular level. These technologies promise to revolutionize fields ranging from geology to medicine, offering insights that were previously impossible to achieve. While the practical applications of superposition are impressive, the concept itself raises profound questions about the nature of reality. If particles can exist in multiple states at once, what does that say about the universe? Some physicists argue that superposition supports the idea of a multiverse, where every possible outcome of a quantum event exists in a separate parallel universe. According to this interpretation, when we observe a particle and force it to collapse into a single state, we are not eliminating the other possibilities. Instead, we are choosing one branch of reality, while the other branches continue to exist in parallel. This multiverse interpretation is both thrilling and unsettling. Not everyone agrees with the multiverse interpretation, and the debate over the meaning of superposition is far from settled. Some physicists favor a more minimalist approach, arguing that superposition simply reflects the limits of our knowledge. In this view, the universe is not inherently probabilistic. It only appears that way because we lack the information to predict its behavior with certainty. Others, like proponents of the Copenhagen interpretation, embrace the idea that observation plays a fundamental role in shaping reality. Regardless of which interpretation is correct, the implications of quantum superposition are undeniable. It has forced us to abandon the comforting certainties of classical physics and embrace a world that is far stranger and more complex than we ever imagined. It has given rise to technologies that are transforming our lives and will continue to do so for decades to come. And it has challenged us to rethink our place in the universe, to question what it means to observe, to measure, and to exist. Quantum tunneling and its profound implications. In the macroscopic world, boundaries are solid and immovable. A ball cannot pass through a brick wall, no matter how hard it is thrown, and a car cannot drive through a closed garage door without destroying it. These everyday observations reinforce our understanding of impenetrable barriers, a concept deeply rooted in classical physics. However, the quantum realm defies this logic with a phenomenon so extraordinary that it challenges the very nature of reality: quantum tunneling. Quantum tunneling occurs when a particle passes through a barrier that, according to classical physics, it should not be able to cross. Imagine a ball rolling toward a hill. If the ball doesn't have enough energy to climb over the hill, it will roll back down. That's the classical view. In the quantum world, however, the ball doesn't always behave as expected. Sometimes it simply appears on the other side of the hill, as if it had tunneled through it. To understand why this happens, we must revisit the concept of quantum superposition. In the quantum world, particles such as electrons are not confined to a single location or state. Instead, they exist as a cloud of probabilities, simultaneously occupying many potential positions. When faced with a barrier, the particle's probability wave doesn't abruptly stop at the edge of the barrier. Instead, it extends beyond it. This means there's a small but non-zero chance that the particle can be found on the other side of the barrier, effectively bypassing the obstacle. One of the most significant applications of quantum tunneling is in semiconductors, the building blocks of modern electronics. Transistors, which power everything from smartphones to supercomputers, rely on the precise control of electron flow through barriers. Quantum tunneling enables electrons to pass through these barriers in a controlled manner, allowing transistors to function with incredible efficiency. This phenomenon is the foundation of the microchips that drive the digital age, making quantum tunneling an integral part of the technology that shapes our lives. Another groundbreaking application of quantum tunneling is in nuclear fusion, the process that powers the stars. In the core of the Sun, hydrogen nuclei fuse to form helium, releasing enormous amounts of energy. However, this process faces a significant challenge. The positively charged hydrogen nuclei repel each other due to their electric charge. Classically, they would need immense energy to overcome this repulsion and come close enough to fuse. Yet, in the Sun's relatively moderate conditions, fusion occurs at a rate sufficient to sustain its brilliance. This is possible because of quantum tunneling. The probability waves of the hydrogen nuclei overlap, allowing them to tunnel through the repulsive barrier and achieve fusion. Without quantum tunneling, the stars in the night sky would not shine, and life as we know it would not exist. One of the most fascinating aspects of quantum tunneling is its connection to time. In classical physics, the passage of time is a continuous, linear progression. However, experiments involving quantum tunneling have revealed hints that time may behave differently at the quantum level. For instance, researchers have observed that particles appear to tunnel through barriers almost instantaneously, as if time itself were compressed during the process. This has led some physicists to speculate that quantum tunneling could offer insights into the nature of time, potentially shedding light on some of the deepest mysteries of the cosmos. Quantum tunneling has also inspired bold new theories about the universe's origins. Some physicists propose that the universe itself may have come into existence through a form of quantum tunneling. According to this idea, the universe emerged from a quantum fluctuation in a vacuum, tunneling through an energy barrier into existence. This theory, known as quantum cosmology, suggests that the same principles governing the behavior of subatomic particles might also apply on the grandest scales imaginable. As we delve deeper into the quantum realm, we are confronted with a universe that is far stranger and more wondrous than we ever imagined. Quantum tunneling is not just a scientific phenomenon. It is a glimpse into a reality where the impossible becomes possible, where particles transcend boundaries, and where the mysteries of existence continue to inspire and astonish us. From quantum theory to breakthrough technologies, quantum mechanics has long been a cornerstone of technological advancement, transcending its origins as a theoretical framework to revolutionize industries and reshape human understanding of the physical world. Today, its applications permeate nearly every aspect of modern life, from the devices we use to communicate to the tools that enable cutting-edge scientific discoveries. One of the most significant contributions of quantum mechanics is the laser, a device that manipulates photons with extraordinary precision. Lasers have transformed medicine through advanced surgical techniques, powered telecommunications with fiber optic networks, and revolutionized manufacturing with precision cutting and welding. Similarly, quantum mechanics underpins the development of semiconductors, the foundation of modern electronics. Without the principles of quantum physics, the transistors that drive computers, smartphones, and countless other devices would not exist. Quantum computing is another transformative technology rooted in quantum mechanics. Unlike classical computers, which process information as binary bits, zeros and ones, quantum computers leverage qubits that exist in a superposition of states. This allows them to perform complex calculations exponentially faster than classical systems, opening new frontiers in fields like cryptography, materials science, and drug discovery. Quantum mechanics has also paved the way for advanced imaging technologies like MRI, magnetic resonance imaging, which rely on the quantum behavior of atomic nuclei in magnetic fields to produce detailed images of the human body. These technologies have saved countless lives and continue to push the boundaries of medical science. As we delve deeper into the quantum realm, the possibilities for practical applications only expand. From quantum-enhanced sensors that can detect gravitational waves to advanced quantum networks that promise instantaneous communication across the globe, the influence of quantum mechanics on technology and society is boundless. The practical applications of quantum mechanics have already transformed the world, but its greatest promise lies in the questions it raises. As we explore the quantum realm, we are not just uncovering the secrets of the atom, we are gaining insights into the nature of life, the cosmos, and our place within it. Will quantum physics prove to be the driving force behind the evolution of life? While the answer remains uncertain, one thing is clear: quantum mechanics is a key to unlocking the deepest mysteries of the universe. It is a testament to humanity's boundless curiosity and our relentless quest to understand the world around us. As we look to the future, quantum mechanics will continue to inspire, challenge, and guide us, shaping the technologies, ideas, and philosophies that define the next chapter of human progress. The journey into the quantum world is far from over. It is just beginning. What is it about the sun that has captivated humanity for millennia? Is it its life-giving warmth, its steady path across the sky, or the cosmic mystery of its origin? Across cultures and ages, the sun has been venerated as a divine presence, an eternal source of power and creation. The myths of the sun, Ra in Egypt, Sol in Norse lore, and the Sun Mother in Aboriginal Australian stories, reflect an intrinsic understanding of its significance, a recognition that science has not diminished, but deepened. Indeed, modern astrophysics reveals a profound truth. The sun is not just a star. It is a thread in a cosmic tapestry of creation and destruction, one that shapes the very essence of our existence. On the surface, the sun's importance is immediate and obvious. Its light and heat sustain life on Earth, maintaining temperatures that allow water to remain a liquid and enabling the complex interplay of ecosystems. Through photosynthesis, plants capture sunlight and transform it into chemical energy, forming the base of the food chain. Herbivores consume this energy, and carnivores consume the herbivores, completing a cycle of life powered entirely by solar energy. Without the sun, Earth would be an icy wasteland, incapable of supporting the rich diversity of life we know today. But the sun's influence extends far beyond its warming rays. Its very existence is tied to a cosmic lineage, a stellar ancestry that connects us to the earliest moments of the universe. The sun itself is a relatively young star, born around 4.6 billion years ago from a dense cloud of gas and dust. This stellar nursery collapsed under the force of gravity, its material compressing until the core became hot and dense enough to ignite nuclear fusion. The remaining matter coalesced into the planets, moons, and other bodies of the solar system. Our Earth, and all life upon it, emerged from this primordial material. Yet, the story does not end there. The gas and dust that formed the sun and its companions were not pristine. They were enriched by the ashes of previous stars. Our sun belongs to a class known as population 1 stars, characterized by their relatively high metallicity, a measure of elements heavier than hydrogen and helium. These elements, such as carbon, oxygen, and iron, are the products of nuclear fusion within earlier generations of stars. The sun's ancestors, population 2 stars, are older and less enriched, containing fewer heavy elements. These stars reside in the Milky Way's galactic halo, ancient clusters that offer a glimpse into the early history of our galaxy. Population 2 stars themselves were born from material created by an even earlier generation of stars, the elusive population 3 stars. These first stars formed from the pristine hydrogen and helium that emerged in the first minutes of the universe during the epoch of Big Bang nucleosynthesis. The population 3 stars were colossal, burning brightly but living brief, tumultuous lives. With no heavy elements to cool their cores, these stars reached immense sizes and temperatures, igniting fusion reactions that forged the first heavier elements. When they died in cataclysmic supernovae, they scattered these newly formed elements into the cosmos, enriching the interstellar medium and seeding the next generation of stars. But even these ancient stellar forges were not the ultimate origin of the elements. To trace our lineage further, we must journey back to the first seconds of the universe, when the cosmos itself was a seething cauldron of energy and matter. During this brief epoch, known as the Big Bang nucleosynthesis, the universe was hot enough for nuclear reactions to occur, creating the lightest elements: hydrogen, helium, and small amounts of lithium. These primordial ingredients formed the foundation upon which all subsequent cosmic chemistry would unfold. It is often said that we are made of star stuff, and this is true in a literal sense. The carbon in our cells, the oxygen we breathe, and the calcium in our bones were all forged in the hearts of ancient stars. Yet this poetic phrase tells only part of the story. We are also remnants of the universe's fiery birth, composed of the hydrogen and helium born in the Big Bang itself. In this sense, the Sun, and by extension all life on Earth, is a direct descendant of the cosmos' primordial furnace. This cosmic recycling continues to shape the universe. The Sun, like all stars, will one day exhaust its nuclear fuel. In approximately 5 billion years, it will expand into a red giant, shedding its outer layers and leaving behind a dense, smoldering core known as a white dwarf. The material ejected by the Sun will enrich the interstellar medium, contributing to the formation of new stars and planets. In this way, the cycle of creation and destruction perpetuates, weaving an unbroken thread through time. The myths of ancient cultures, which viewed the Sun as a creator and sustainer, resonate deeply with the scientific understanding of its role in the cosmos. The Sun is not just a god in metaphor, but a divine force in the literal sense, shaping the earth and fueling life, while embodying a lineage that stretches back to the dawn of time. As we gaze upon it, we are not merely observing a star, we are witnessing a link in a cosmic chain, a reminder that our existence is part of a grand, interconnected story that spans the universe. In 1782, James Price, a 30-year-old chemist and newly inducted member of the Royal Society, made an extraordinary claim. He had reportedly developed powders capable of turning mercury into silver and gold. A white powder, he said, could convert a gram of mercury into 50 grams of silver, while a red powder could transform it into 60 grams of gold. Unlike typical charlatans of the time, Price demonstrated his experiments to witnesses, gaining both public attention and an honorary medical degree from Oxford, though not explicitly for these claims. Price's assertions, however, met skepticism among his peers. The Royal Society demanded he replicate his experiments under scrutiny, but Price demurred, citing health concerns and the impracticality of the process. He argued that the cost of creating the powders exceeded the value of the resulting metals. Under increasing pressure, he agreed to a public demonstration in January 1783. Tragically, rather than attempt to replicate his alchemy, Price consumed a vial of laurel water and died, leaving his claims unproven. Yet, the dream of transmutation did not die with Price. The desire to transform one element into another resurfaced in the work of Ernest Rutherford, the so-called father of nuclear physics. Born in New Zealand in 1871, Rutherford's scientific journey took him from a small-town education to the University of Cambridge, where he became the first non-graduate student researcher. His groundbreaking work in radioactivity began at McGill University in Canada. In 1901, Rutherford and his colleague Frederick Soddy observed thorium slowly decaying into radium. Soddy exclaimed that the element was undergoing natural transmutation, to which Rutherford famously replied, "For Mike's sake, Soddy, don't call it transmutation. They'll have our heads off as alchemists." Yet, this observation marked the first scientific confirmation that elements could transform into one another. By the 1920s, Rutherford had demonstrated that bombarding nitrogen atoms with alpha particles produced hydrogen. His student, Patrick Blackett, captured this process in 1925 using a cloud chamber, providing definitive proof of element transmutation. Blackett's achievement was recognized with the Nobel Prize in Physics in 1948. Though far from the gold sought by ancient alchemists, this marked a milestone. Humanity had intentionally transformed one element into another. Rutherford later remarked that while modern methods could produce gold through the transmutation of platinum, the process was exceedingly inefficient and expensive. This ushered in an era where the subatomic world, composed of protons, neutrons, and electrons, became the focus of scientific exploration. elements can change identity through radioactive decay, nuclear fission, or nuclear fusion. In radioactive decay, an unstable nucleus emits particles, transforming into a lighter element. Fission, often harnessed in nuclear power plants and weapons, involves splitting heavy nuclei into smaller fragments. Fusion, by contrast, combines lighter nuclei into heavier ones, releasing immense energy. Fusion lies at the heart of stars, including our Sun. The Sun's core reaches temperatures of 15 million degrees Celsius, where intense gravitational pressure enables hydrogen nuclei to overcome their electromagnetic repulsion and fuse into helium. This process releases energy that powers the Sun and produces heavier elements over time. On Earth, achieving fusion requires even higher temperatures, around 150 million degrees Celsius, due to the lack of stellar gravitational pressure. Despite these challenges, scientists continue to pursue nuclear fusion as a source of energy. Fusion offers the potential for a virtually limitless and clean energy supply, mirroring the processes that sustain stars and create the elements of the universe. It is a quest that connects humanity's ancient aspirations with cutting-edge science, seeking to harness the same forces that illuminate the cosmos. What powers the Sun, and by extension, the countless stars that dot the cosmos? How does this process sustain such brilliance over billions of years? For centuries, these questions captivated humanity, and in 1920, English astronomer and physicist Arthur Eddington challenged his peers to reconsider their understanding of stellar energy. At the annual meeting of the British Association for the Advancement of Science in Cardiff, Eddington confronted the prevailing explanation: gravity. Scientists believed that the Sun's immense heat originated from the gravitational collapse of gaseous matter. However, this theory failed to align with the known age of the Earth and the solar system, which were already measured in billions of years. By their calculations, the Sun would have burned out after only 20 million years. Eddington dismissed this outdated hypothesis as an unburied corpse. Instead, Eddington proposed a groundbreaking idea: the Sun's energy derived from subatomic processes. A star is drawing on some vast reservoir of energy by means unknown to us, he speculated, suggesting that deep within the Sun, hydrogen was fusing into helium. This nuclear fusion not only explained the Sun's longevity, but also hinted at the cosmic role of stars as factories of heavier elements, the building blocks of our world. Eddington estimated that such subatomic processes could sustain the Sun for 15 billion years, a figure close to the modern understanding. This realization was not just a theoretical triumph, it carried profound implications for humanity. Eddington foresaw that nuclear fusion could be harnessed either for great benefit or catastrophic destruction. Over the next century, scientists pursued both paths, unlocking the secrets of stellar alchemy. One key to understanding fusion lies in the study of brown dwarfs, often referred to as failed stars. These celestial bodies, dim and elusive, occupy the boundary between gas giants like Jupiter and the smallest stars. Lacking sufficient mass to sustain the proton-proton fusion that powers true stars, brown dwarfs rely on a different form of nuclear fusion, the fusion of deuterium. Deuterium, an isotope of hydrogen, contains one proton and one neutron, making it slightly easier to fuse than protium. Deuterium's abundance varies. In Earth's seawater, there is approximately one deuterium nucleus for every 5,000 protium nuclei, while in Jupiter's atmosphere, the ratio drops to about 1 in 40,000. This natural abundance has inspired scientists to explore deuterium-based fusion as a potential energy source. Modern fusion research seeks to replicate these processes on Earth. One of the most promising approaches involves combining deuterium with tritium, another hydrogen isotope that contains two neutrons. This reaction produces helium-4 and releases a lone neutron, which carries 80% of the energy generated. In August 2021, researchers at the National Ignition Facility, NIFE, in California, achieved a milestone, fusing 200 micrograms of deuterium and tritium to produce an astonishing 10 quadrillion watts of power. Though the burst lasted only 100 trillionths of a second, it represented a record for energy efficiency in fusion reactions, with 70% of the input energy recovered. Despite this progress, significant challenges remain. For fusion to become a viable energy source, it must achieve two critical goals: producing more energy than it consumes and sustaining reactions for meaningful durations. Current methods, while impressive, fall short of these benchmarks. The International ITER project in France aims to address these hurdles by constructing a fusion reactor capable of producing 10 times the energy it consumes. Expected to activate in 2025, ITER represents humanity's most ambitious effort to harness fusion power. However, even ITER's success would not mark the end of the journey. Deuterium-tritium fusion, while relatively accessible, has limitations. The process generates neutrons, which complicate energy capture and pose safety challenges. Alternatives like helium-3 fusion offer cleaner byproducts but require higher temperatures and rarer fuel. Helium-3 is believed to exist in significant quantities on the Moon, deposited over billions of years by solar winds. Mining this isotope could spark a new space race, further intertwining the quest for fusion with humanity's exploration of the cosmos. Fusion's potential extends far beyond energy generation. It mirrors the processes that sustain stars and create elements, linking humanity's scientific pursuits to the grand cycles of cosmic evolution. Before stars, supernovae, and even the first galaxies, there was a brief epoch when the entire universe acted as a fusion reactor. In those first moments after the Big Bang, nuclei fused in a searing crucible of energy, forging the lightest elements and setting the stage for everything that followed. Big Bang nucleosynthesis. The story begins not with stars, but with an explosion, the Big Bang. In its immediate aftermath, the universe was a seething soup of energy, where particles and antiparticles sprang into existence and annihilated each other almost as quickly. As the universe expanded, it began to cool, but even this cooling phase was unimaginably violent by today's standards. Within the first microsecond, temperatures had dropped to a blistering 10 trillion degrees Celsius, allowing quarks to bind together into composite particles called hadrons. Hadrons, the building blocks of atomic nuclei, emerged in two primary forms: protons and neutrons. These particles formed from combinations of up and down quarks, whose whimsical names belie their cosmic significance. Two up quarks and one down quark formed a proton, while one up quark and two down quarks created a neutron. Together, these particles laid the foundation for Big Bang nucleosynthesis, the process by which the first elements were forged. By the time this nucleosynthesis began, roughly one neutron existed for every 7 protons. This ratio, shaped by the slight mass difference between protons and neutrons and the rapid cooling of the universe, would profoundly influence the chemical makeup of the cosmos. Neutrons, being slightly heavier and less stable than protons, decayed into protons, electrons, and neutrinos unless bound within atomic nuclei. As a result, the available neutrons were soon limited, setting a cap on how much helium and other elements could form. The first critical step in this cosmic alchemy was the creation of deuterium, an isotope of hydrogen consisting of one proton and one neutron. However, the universe faced a bottleneck. Temperatures were still so high that collisions with energetic photons often broke apart deuterium nuclei almost as soon as they formed. Only after about 300 seconds, when the universe had cooled sufficiently, did deuterium become stable enough to survive. This breakthrough allowed the synthesis of helium to begin in earnest. Helium-3, a nucleus composed of 2 protons and 1 neutron, was one of the first products of this process. But the most stable and abundant form of helium, helium-4, required 2 protons and 2 neutrons. The strong nuclear force, which binds protons and neutrons together, overcame the repulsive electromagnetic force between protons to create this exceptionally stable nucleus. Helium-4's stability made it the most favored product of nucleosynthesis, second only to the simplest hydrogen nucleus, a lone proton. While deuterium and helium-4 were the primary products, trace amounts of lithium and beryllium also formed. Lithium-7 and beryllium-7 emerged in small quantities, but beryllium-7 quickly decayed into lithium-7. The absence of stable isotopes with 8 nucleons, combined with the rapidly cooling universe, prevented the formation of heavier elements. By the time the universe was 20 minutes old, nucleosynthesis had effectively ended, leaving behind a primordial composition of approximately 75% hydrogen, 25% helium, and a trace of lithium by mass. These were the only elements present in the early universe. Heavier elements, the carbon in our cells, the oxygen we breathe, the iron in our blood, would have to wait for the first stars to form. These population 3 stars, composed almost entirely of hydrogen and helium, ignited the next chapter of cosmic evolution. Through nuclear fusion in their cores, these stars forged new elements, and in their deaths, seeded the universe with the materials necessary for planets, life, and complexity. Yet, even the pristine simplicity of the early universe holds mysteries. In 2013, astronomers made a puzzling measurement that seemed to challenge our understanding of Big Bang nucleosynthesis. By studying ancient stars and comparing their chemical compositions to theoretical predictions, they uncovered discrepancies in the observed abundances of certain elements. These anomalies suggest that the early universe may still hold secrets, forcing scientists to refine their models and search for new answers. The story of Big Bang nucleosynthesis is not just a tale of the universe's infancy, it is the foundation of everything we see around us. From the smallest atom to the largest galaxy, the legacy of those first moments continues to shape the cosmos. In understanding it, we come closer to unraveling the ultimate origins of matter and the universe itself. The cosmological lithium problem. What happens when our understanding of the universe doesn't align with the evidence we observe? What if one star could challenge the very framework of cosmic history? These questions come into sharp focus when we consider HD 140283, popularly known as Methuselah, a star whose age once appeared to exceed that of the universe itself. Methuselah, located a mere 109 light-years away in our galactic neighborhood, initially baffled astronomers with an estimated age of 14.5 billion years. This figure, greater than the universe's age of 13.8 billion years, seemed impossible. Yet upon closer examination, uncertainties in measurements revealed the true story. When the margin of error was accounted for, Methuselah's minimum possible age aligned more comfortably at 13.66 billion years, and subsequent studies have suggested it may be younger still, possibly as young as 11.5 billion years. While we may never pinpoint Methuselah's exact age, its composition offers invaluable insights into the early universe. Methuselah is a population 2 star, part of a generation that formed shortly after the first stars, known as population 3, lived and died. These ancient stars provide a window into the primordial universe, as their low metallicity reflects the scarcity of heavier elements in their formation. As stars live and die, they contribute to cosmic nucleosynthesis, enriching the interstellar medium with heavier elements. Over generations, this stellar alchemy has led to the metal-rich stars of today, classified as population 1. Methuselah's composition situates it among the earliest population 2 stars, making it a crucial target for understanding the transition from the first stars to the universe we see now. To probe even deeper into cosmic history, astronomers study not only individual stars like Methuselah, but also the least massive, irregular dwarf galaxies. These galaxies, with their limited star formation and low metallicity, serve as time capsules, preserving the elemental ratios from the universe's first half hour. Observing such systems allows scientists to compare these primordial ratios with the predictions of Big Bang nucleosynthesis models. For the most part, these comparisons agree remarkably well. The predicted abundances of hydrogen, including its isotope deuterium, and helium-4 match observations closely. However, lithium-7 remains a glaring exception. Observations consistently show far less lithium-7 than theoretical models predict. This discrepancy, known as the cosmological lithium problem, poses one of the most enduring mysteries in astrophysics. The creation of lithium-7 is intricately tied to the conditions of the early universe. Its abundance depends on the ratio of photons to protons and neutrons during Big Bang nucleosynthesis, a value derived from observations of the cosmic microwave background, CMB. The CMB, the oldest light in the universe, provides a precise measurement of this ratio, allowing scientists to calculate the expected quantities of primordial elements. While these calculations align for hydrogen and helium, they predict 3 times more lithium, 7 than is observed. To resolve this conundrum, scientists have proposed 3 potential explanations. The first looks to stars themselves. Observations of stellar atmospheres provide indirect measurements of lithium-7, but stars are adept at destroying lithium through fusion processes. It's possible that much of the primordial lithium has been consumed or sequestered within stellar interiors beyond the reach of our telescopes. Additionally, determining a star's internal temperature is complex, and small errors can amplify discrepancies in inferred lithium abundances. The second explanation lies at the nuclear level. The processes that govern the formation and decay of nuclei, including beryllium, may not be fully understood. If beryllium-7 forms less readily or decays differently than current models suggest, this could account for the observed shortfall in lithium. A 2015 study explored these nuclear reactions, but only deepened the mystery, widening the gap between theoretical predictions and observational data. The third and most radical explanation questions the fundamental assumptions of cosmology. Theoretical models of Big Bang nucleosynthesis rely on our understanding of the universe's physical laws and initial conditions, including the 4 fundamental forces and the properties of subatomic particles. However, known gaps in these models, such as the existence of massive neutrinos and dark matter, suggest that our picture of reality may be incomplete. Exotic particles or unknown physics could have influenced the early universe in ways we have yet to uncover. Another possibility is that the universe is not as homogeneous as assumed. Cosmological models operate under the principle that on large scales, the universe appears uniform. But if our region of the cosmos is less dense than the average, this could bias our measurements and interpretations. Such a deviation could subtly alter the inferred elemental abundances, offering a potential resolution to the lithium problem. Addressing the cosmological lithium problem requires advancements on multiple fronts. Improved telescopes and observational techniques will refine measurements of stellar compositions, while sophisticated computational models will provide deeper insights into nuclear processes and cosmological conditions. As new data emerges, scientists may yet uncover the missing pieces of this cosmic puzzle. Ultimately, the lithium problem underscores the profound challenges of understanding the universe's earliest moments. It is a testament to humanity's relentless pursuit of knowledge that we can probe questions of such magnitude, questions that stretch back to the very beginning of time. From the chaotic quark-gluon plasma of the Big Bang to the formation of the first stars and galaxies, the journey of cosmic evolution is a story of complexity emerging from simplicity. And as we continue to explore this story, we edge closer to comprehending the forces and processes that shape the universe we call home.